Hello everyone, welcome to the 11th video of our lecture series. So in the previous video we are talking about addition of angular momentum. So we talked that if we have two angular momentum J1 and J2, then their product space, which is of dimension n, which has dimension 2j1 plus 1 into 2j2 plus 1. So this product space, it can be represented either by the basis of j square, jz, j1 square and j2 square, or we can represent this in the basis of j1 square, j1z, j2 square and j2z. So the basis in which these four are simultaneously diagonalized, it is represented as j, m, j1, j2, and the basis in which these four operators are simultaneously diagonalized, they are represented by j1, m1, j2, m2. Now since this j1 and j2 are fixed, we can represent this in shorthand notation as jm. So we have to and we also stated that this state and this state, they are related by Clebsch-Gordon coefficient. So we can write this jm as, so we can write this jm to be j1 m1, j2 m2, j1 m1, j2 m2, and we have jm. So this is our Clebsch-Gordon coefficient, and through this coefficient we can connect these two basis states. So and the summation is over m1 m2. So now let us proceed. So we have to so in the problem we have to find the eigenvalues of j square and jz. So and which is in terms of j1 square, j2 square, j1z and j2z. That means we have to express jm in terms of j1, j2, m1 and m2. Now we know that what is the maximum value of m1? Maximum value of m1 is j1, because j1 is fixed and m1 can have values from minus j1 to plus j1, and similarly maximum value of m2, it can also be j2, because in the same logic m2 can have values from minus j2 to plus j2, and j1 j2 they are fixed. So so maximum value of m1 is j1 and maximum value of m2 is j2. Now we also know that jz is summation of j1z plus j2z, because we know j is j1 plus j2, so the z component will be add up. So we can write this jz component is our m, and we have our m1 and m2. Now what will be the maximum value of this? It will be the summation of the maximum value of m1 and maximum value of m2. That means m can have maximum value of m1 max and m2 max, but this m1 max is what? M1 max is j1 and m2 max is j2. So maximum value of m, it can be j1 plus j2, but we know that m value must be less than equal to z. M value cannot be greater than j. So So we can write the maximum value of M to be equal to Z. That is the maximum case. So what will be the Z maximum? Z maximum must be equal to J1 plus J2, because this J value is not fixed, but whatever the Z value is, the maximum value of allowed M is J1 plus J2. So and maximum M max can be equal to J. So Z maximum can have maximum value of J1 plus J2. So this is our maximum value of J. Now we have to find the minimum value of J. That means Z minimum. So how we will find this? To find this, we have to use the fact that there are 2J1 plus 1 into 2J2 plus 1 eigenket Jm. So how we are writing this? We know that this Jm belong to the product space, and product space has dimension of 2J plus 1 into 2J plus 2. So that is why they must be spanned by 2J plus 1 into 2J plus 2J1 plus 1 into 2J2 plus 1 eigengets. This we can easily write, because suppose we have 3-dimensional coordinate. So since it is in 3D, so we need 3 eigengets to span any vector here. So in the same logic, the product space has dimension of 2J1 plus 1 into 2J2 plus 1. So that is why we need this number of eigengets to span the product space. So this is our maximum number of eigengets. Also, we know that for each J, there are 2J plus 1 eigenstates Jm. Because for each J, M value can run from minus J to plus J. So for each J, we have 2J plus 1 M values. So that is why 2J plus 1 eigenstates of this. So we can easily write that 2J plus 1, this value is for 1J, and what can be the different J values? J can run from J minimum to J maximum. So this much eigengets are possible for this state, but we know this should be equal to the dimension of the product space. So that is, this must be equal to 2J1 plus 1 into 2J2 plus 1. So from this formula, from this we can calculate the Z minimum. So let us calculate this. So we know that maximum value of Z is J1 plus J2. So if we consider this summation to be S, so what will be S? S is from J runs from J minimum to J maximum 2J plus 1. So this can be written as 2J minimum plus 1, 2J minimum plus 3, 2J minimum plus 5, and so on. And in the way, what will be the last term? It will be 2J maximum plus 1. So we have this summation. So we can write this as 2J1 plus J2 plus 1. So this is our first term. Second term will be 2J1 plus J2 minus 1. plus 2 j1 plus j2 minus 3, and in the similar manner what will be the last term? 2j minimum plus 1. So here we are starting from our minimum and going to maximum, and here we are starting for our maximum and we are going to minimum. So this is also S. So if we add up these two terms, what we will get? We will get 2S equal to, so we add this term. So so if we add, we will have 2 j1 plus j2 plus 1 plus j minimum, and what will be the second term? Second term will be j1 plus j2 plus 1 plus j minimum. Third term will be 2 j1 plus j2 plus 1 plus j minimum. So all the terms will be this, and the last term will also be 2 j1 plus j2 plus 1, and we have j minimum. So how many these terms are there? So this expression have this j1 plus j2 plus 1, these terms. Now this expression have j max minus j min plus 1 terms. So that means j1 plus j2 plus 1 minus j minimum, because it is starting from the j minimum and we are going to j maximum in steps of 1. So that is why there are this many terms are there in this expression. So this number of terms. So we can write 2s as 2 into j1 plus j2 plus 1 plus j minimum into how many terms? j1 plus j2 plus 1 minus j minimum. This much number of terms. So we can write this as, this expression can be written as j1 plus j2 plus 1 squared minus j minimum squared, because this is a plus b and a minus b. So s can be write as this. So this is equal to the dimension of the product space. So this is equal to 2j1 plus 1 into 2j2 plus 1. So let us expand this. So we have j1 squared plus j2 squared plus 2j1 plus 1 plus 2j1 j2 plus 2j1 minus j min square. So it will be 2j2, and here we have 4j1 j2 plus 2j1 plus 2j2 and 1. So these 2j1 2j2 terms, they will cancel out and what we will have, this one term will also cancel out. So we have j min squared equal to j1 square plus j2 square minus 2 j1 j2. So j minimum squared is equal to j1 minus j2 squared. So j minimum is the modulus value of this j1 minus j2. So we got our minimum value and we also got our maximum value. So what is the range of j? So j can run from j1 minus j2, its mod value, to j1 plus j2. and so in steps of 1. So j have values of j1 minus j2, j1 minus j2 plus 1, and what will be the last two terms? It will be j1 plus j2 minus 1 and j1 plus j2. So let us consider an example. So suppose we have j1 to be 2 and j2 to be 5. So what will be the possible values of j? So it can be from 3, 4, 5, 6, 7. And what is the minimum value? Minimum value is the difference between these two. So j minimum is 3. And what is the maximum value? Maximum value is the addition of these two. So maximum value is 5. So in this way, if we are given two angular momentum from the from the addition of angular momentum, we can calculate what will be the angular momentum of the product space. So the product space can have angular momentum of these values. Okay, so now let us find the coefficients, the Clebsch-Gordon coefficients J1, J2, M1, M2 with Jm. So first, notice that this coefficient will vanish unless m equal to m1 plus m2. So let us prove this. So we know that Jz is J1z plus J2z. So from here we can write J1z plus J2z minus Jz equal to 0. So if we find the expectation value of this, so or not expectation value, so you can so this value of this operator Z1z plus Z2z minus Jz Jm. So if we want to find the value of this, so what will this do? This will operate on this and it will give us value m1. Similarly, this will operate on this and will give the value m2, and this will operate on this and will give the value m. So we have this and J1, J2, m1, m2, Jm. So this is 0. That means we have two possibilities. Either this is 0 or this is 0. So when this is 0, this will be 0 when this is not 0, and this will only exist when this will be 0. That means m1 plus m2 minus m 0. So m equal to m1 plus m2. So for that case only, in that case we have this J1, J2, M1, M2, Jm to be non-zero. So what we have learned? So we have learned that for the Clebsch-Gordon coefficient not to be 0, we must simultaneously have m equal to m1 plus m2 and j value is between j1 minus j2, j1 plus j2. So when we have simultaneously satisfied these two conditions, then only our Clebsch-Gordon coefficient is non-zero. So this is known as selection rule for the Clebsch-Gordon coefficient. So we have find out the selection rules. Now we are all set to calculate the Clebsch-Gordon coefficient. So calculation of the Clebsch-Gordon coefficient. So let us do. So first we should point out that this Clebsch-Gordon coefficient. So let us first calculate the Clebsch-Gordon coefficient for the two limiting cases. So what are the limiting cases? First limiting case is we have M1 value to be J1, M2 value to be J2, J have value J1 plus J2, and M have value J1 plus J2. So, and what is the second limiting case? Second limiting case is that M1 have value minus J1, M2 have value minus J2, J is have value J1 plus J2, and M have value minus J1 minus J2. So that means we are considering the maximum values of M and minimum values of M for the maximum value of J. So so you can see that the coefficient for these two limiting cases, the Clebsch-Gordon coefficient should be equal to 1. That means J1, J2, J1, J2, J1 plus J2. So this is our J value and this is our M value. So this will be 1 and J1, J2 minus J1 minus J2, and here we have J value to be J1 plus J2 and M value to be minus J1 plus J2. So this is our so these two coefficients, this must be 1. So why? So because this J1 J2 J1 J2 this state and J1 plus J2 minus J1 plus J2, these two terms, these have only one element each. So that is why we can write J1 plus J2 to be J1 J2 J1 J2 J1 plus J2 J1 plus J2, and we have here J1 J2 J1 J2, and similarly we have J1 plus J2 minus of J1 plus J2. This must be equal to J1 J2 J1 J2. Here we have J1 plus J2 J1 plus J2 and J1 J2, and here we have J1 J2. So this is coming from the relation which so from here, because we know that for the limiting cases these two terms can have only one element. This M1 M2, they are maximum values, so that is why the Clebsch-Gordon coefficient corresponding to the two limiting cases must be 1. And the calculation of the other coefficients, they generally involve the two limiting cases. So for this we need to use the recursion relation. So basically what we will do, we know that when J1 and J2, these two are fixed and also J is fixed. So let us consider this condition, that we have a fixed J and J1 J2 are always fixed. So the Clebsch-Gordon coefficients, they are related to one another by means of the recursion relation. So to find the recursion relation, we need to evaluate the matrix element J1, J2, M1, M2, J plus minus Jm. So we can calculate this value in two different ways. So we can calculate this in two different ways. So first, what we can do, we can allow this J plus minus to act on the right side Jm, and secondly we can express this J plus minus in terms of J1 plus minus and J2 plus minus, and we can act them on the state to the left. So first consider acting of this on right side. So what will be the value? So we have J1, J2, M1, M2, J plus minus Jm. So if this act on this, we will have the value h cut root under J minus plus M, J plus minus M plus 1, and we will have this. We are operating this on this, so this state will remain as it is, M1, M2, but this state will have the value J, M plus minus 1. Now if you add this J plus minus on this right side, so let us do that. So we can express this J as summation of J1 plus minus and J2 plus minus. So if we evaluate this expression in terms of this, we will get J1, J2, M1, M2. Here we have 1 plus minus, 2 plus minus, and Jm. So now this will act on this and this will act on this. So we will get h cut root under J1 plus minus M1, J1 minus plus M1 plus 1. What will be the state? We are operating on first subspace. So we will have J1, J2. Now M value will be M1. M value will be M1 plus minus 1. M2, Jm, and for the second term, if we add this, we will have the value h cut root under J1 plus minus, sorry, this will be J2. We are operating on second subspace, so J2 plus minus M2, and here we will have J2 minus plus M2 plus 1, and we will have J1, J2, M1 will be same, and M2 will be M2 plus minus 1, and we have Jm. Okay, so this will be M1 plus minus 1 and M2. So this is our so this expression and this expression, they must be same. Okay, so this should be minus plus. So because we are operating this on kth state, so we are not operating on brass state. So that is why we will have here M1 minus plus 1, and this will be M2 minus plus 1. So if we equate these two, then we will get root under J minus M minus plus M and J plus minus M plus 1, J1, J2, M1, M2, J, M plus minus 1. This will be equal to root under J1 plus minus m1, j1 minus plus m1 plus 1, and here we have j1, j2, m1 minus plus 1, m2, jm, and another term we will have root under j2 plus minus m2, and j2 minus plus m2 plus 1, and this coefficient. So this relation together with the orthonormalization relation that we already have, this will determine all the Clebsch-Gordon coefficients for any given values of j1, j2 and z. So to see this, so let us substitute m1 equal to j1 and m equal to j in the lower part of this equation. We are substituting m1 as j1 and m as j. So now m2 can be equal to only m2 j minus j1 minus 1. Why it is this? Because we know that j value, maximum of j value can be j1 plus and j2. So from that we can conclude that m2 can be j minus j1 minus 1. So if we replace this, we have root under 2j, j1, j2, j1, and m2 value is j minus j1 minus 1, and here we have j minus 1. So it will give us root under j2 minus j plus j1 plus 1, j2 plus j minus j1, and it is with the products with the coefficient j1, j2. Here we have j1 and j minus j1 with j. So if we know this j1, j2, if we know this, then we can determine this. So in this way we can calculate all the Clebsch-Gordon coefficients. So in addition, if we substitute m1 equal to j1 and m equal to j minus 1 and m2 equal to j minus j1 into the upper part of this equation, then we will end up with root under 2j. Here we have j1, j2, j1, j minus j1, j. Then we will get root under 2j1, j1, j2, j1 minus 1, j minus j1, and we have j minus 1, plus we will have another term which will be root under j2 plus j minus j1 and j2 minus j plus j1 plus 1 all are under root, and we have j1, j2, j1, j minus j1 minus 1, j minus 1. So thus by knowing this, j1, j2, j1, j minus j1, jj, this term, and j1, j2, j this term. So if we know this, we can determine this j1, j2, So if we know this term and this term, we can determine this, and using this repeated application of this recursion relation, that equation, if we apply this repetitively, then from this we will determine all other Clebsch-Gordon coefficient. So by repetitive application, so let us denote this equation by 1. So repeated application of the recursion relation of equation 1, this will determine all other Clebsch-Gordon coefficient. Provided we know only one of them. So let us suppose this is, we know this J1, J minus J1 and JJ. So with the recursion relation, and with the help of equation 1, if we know this this term, so then we can find all other Clebsch-Gordon coefficient. But how can we determine the sign? Because this relation determines all the Clebsch-Gordon coefficients except for a sign. So the convention is known as phase convention. So phase convention is to, so it is stating that the phase convention is to consider this J1, J2, J1, J minus J1 and JJ, this to be real and positive. So the phase convention implies that J1, J2, M1, M2, Jm, this coefficient will be equal to minus 1 to the power j minus J1 minus J2, J2, J1, M2, M1, Jm. So hence we have J1, J2, M1, M2, Jm. This must be equal to minus 1 to the power j minus J1 minus J2, and here we have J1, J2 minus M1 minus M2, Jm. So this is equal to J2, J1 minus M2 minus M1, Jm. So for one thing you have to notice is that since all the Clebsch-Gordon coefficients, they are obtained from a single coefficient, this J1, J2, J minus J1 and JJ, all the Clebsch-Gordon coefficients are obtained from the single coefficient, and since this coefficient is real, all other Clebsch-Gordon coefficients must be real. This is real, so it implies that all other so this implies all other Clebsch-Gordon coefficient must be real number. So now if we follow the same method that we did to get our equation 1, and if we follow the same method, so that from equation 1 we can show, so through a rigorous calculation we can show that this j minus plus m plus 1, j plus minus m, j1, j2, m1, m2, jm. This must be equal to root under j1 plus minus m1, j1 minus plus m1 plus 1, and we have j1, j2, m1 minus plus 1, m2, j m minus plus 1 plus root under j2 plus minus m2 and j2 minus plus m2 plus 1, and here we have j1, j2, m1, m2 minus plus 1, and we have j m minus plus 1. So we can use the equation 1, and if we denote this by equation 2, so we can use these two relations to obtain the values of the various Krebs-Gordon coefficient. So for instance, so if we insert m1 equal to j1 and m2 equal to j2 minus 1 and j as j1 plus j2, m as j1 plus j2, then from the into the equation 1, then we will obtain, you can do this just by inserting this j1, j2, here we have j1, j2 minus 1, j1 plus j2, j1 plus j2 minus 1. So this will be root under j by j1, j2 by j1 plus j2, and similarly if we substitute m1 as j1 minus 1, m2 as j2, j as j1 plus j2, and m as j1 plus j2 into the lower sign of equation 1, then it will lead to j1, j2, j1 1, j2, j1 plus j2, j1 plus j2 minus 1. This will be root under j1 by j1 plus j2. So this way we can calculate all the Krebs-Gordon coefficient if we know any one of the coefficients. In a future video, I will give an example of how to find this Krebs-Gordon coefficient. So in that case, that will be much more clearer to you. Okay, so that is it today's video. So we will meet on our next lecture video.